Hi everyone, welcome back to another OneClass session. My name is Bassam and I'm an engineering graduate, and today we're going to be going through some math problems at the high school and university level. So let's get started over here. So the first question here we have, let's open up this image. It will give us probably more information. Okay, so here we have a let t in the real domain and with three coordinates be the linear transformation to a two vector kind of coordinate system. So here we have the 3 and 2, so it's indicating that we're converting kind of a 3 component vector to a 2 component vector in some domain. So here we have to use a linear transformation to solve for t to 1, 1, negative 2, and we're given these two transformations to use, and we're given 5 options. So let's write the question over here. So the transformations that were given are as follows. So we have to find for this transformation. So we're trying to solve for this, and we're given two transformations. So 1, 0, negative 1 equals 5, negative 2. And we're also given 0, 1, negative 1. Let me just double check that. Yep, 0, negative 1, negative 1 equals 1, 2. So to solve for this problem, we have to know one property of a linear transformation. This is as follows. So t, if we have some vector u plus some vector v is equal to the transformation of vector u plus transformation of vector v. So we're going to use this property to solve for this. Okay, so one thing we can kind of recognize here is looking at one thing at a time. So if we look at the first component, so we have 1 over here, we have 1 over here, and then we have a 0 over here. So we can see if we did, let's call this transformation 1, and let's call this transformation 2. So if we did the first transformation, 1, plus 0, we would get the 1 up here. So we get the 1 up here. If we did, let's say, the second component, 0 plus 1, we would get also the 1. And then if we did negative 1 plus negative 1, we would get negative 2. So we can kind of see how this applies here. So if we added kind of these two together, we will be able to solve for the transformation here. Okay, so let's write out the following. So we can pull this down a little bit, and we can say that this transformation, we can kind of split it up into two vectors. So we'll have 1, 0, negative 1 plus 0, 1, 1. Sorry, negative 1 down here. So we can see how this is equivalent to this. And this will help us use the two transformations below, this one, number 1 and number 2, to solve. So we'll use this property to simplify the equation a little further. So we'll keep going over here. So we'll say t to 1, 0, 1 plus t 0, 1, negative 1. So we got these two. So we go back and we can see we can just kind of sub this in and sub this in to find the solution. So subbing those two values in, I'll just close them off. So here we have the first one is 5, negative 2. And then the second one is 1, 2. And we just got them from over here. These were given from the question. So they're given here in the question, and we just have to solve for this now. So just give me a second, let me just move this over. So solving for this, we would get 5 plus 1 would give us 6, and negative 2 plus 2 would give us 0. So this right here is our solution. So from the solutions A, B, C, D, E, 6 and 0 is present in B, and we know B is the correct answer. So the correct answer is B for linear transformation. So here the student presents an incomplete solution. So incomplete solution, correct answer selected, need to show work. So here the solution is incorrect because there's no steps to finding that the answer is B. Okay, so the next question is asking us to convert the equation x squared plus y squared equals 2x. So I'm looking at the solution here, and they use x squared plus y squared, so it's not just 2x. So x squared plus y squared equals 2x. And we need to convert this into polar coordinates. So to do this conversion, we have to know the following. We have to substitute for x, r cos theta, and for y, we substitute r sine theta. So whenever we're converting from xy coordinates to polar coordinates, this is the substitution that we will do. So we'll sub in for x, so we have r cos theta squared plus r sine theta squared is equal to 2 and then r cos theta. So this will give us r squared cos squared theta plus r squared sine squared theta equals 2r cos theta. So we can see we can factor out the r squared. So r squared cos squared theta plus sine squared theta equals 2r cos theta. We know this is a trig identity, and this just equals 1. So that means this simplifies to r squared equals 2r cos theta. And we can divide by r on both sides, so we'll actually end up with r equals 2 cos theta. And this is our final answer to converting the equation to polar coordinates. So we'll look at the attempted solution. So they do the correct substitution for x and y, and they simplify it down using the trig identity to get r 2 cos theta, and this is the correct form. correct answer. Great job. So here we're asked, what does x equal? We're not given much information. So here the solution outlines trig ratios and kind of angles for triangles. So what we can do here is kind of just go over generally the fundamental trig ratios to know and the special triangles. So we know that we have the mnemonic so ka toa. This just means that so is sine theta equals opposite over hypotenuse. So that's the first one. And then we have cos theta is adjacent over hypotenuse, and then tan theta is opposite over adjacent. So I'll underline where this, so here we have the S is sine, OH is opposite over hypotenuse, C is cos, AH is adjacent over hypotenuse, T is tan, and we have OA for adjacent over hypotenuse. So this is for a right angle triangle. So if we had a right angle triangle like so, and we were trying to solve for theta, this would be the opposite side, this would be the adjacent side, and this would be hypotenuse. And the reciprocals of of sine, cos, and tan would give us the following. So cosecant theta is actually 1 over sine theta, and this just equals hypotenuse over opposite. And then secant theta equals 1 over cos theta, and this equals hypotenuse over adjacent. And finally, cotangent theta is 1 over tan theta, which equals adjacent over opposite. So these are kind of the fundamental ones to know for trig ratios when we're solving for theta. Let me just check something over here. All right. Just give me a second. Okay, so secondly, what we also should know, or an important kind of fact to know, are the special triangles. So there's two. We have the first one, which has a right angle over here, and then we have a second one that's a little bit longer and has a right angle over here. So this is useful whenever we're solving any kind of problem that has triangles. So for this triangle, we have 1 square root 2, and then this angle is 45 degrees, and then this angle is 45 degrees. And the second special triangle is 1, 2, square root 3, and this angle is 30 degrees, this angle is 60 degrees. So we can see how SOHCAHTOA might come in handy here. So let's say we're looking at this angle. So if you wanted to say what is sine 45 degrees, we know it's opposite over hypotenuse. So opposite, which is 1, so this is 1, over square root 2, square root 2. So that's the easy way to evaluate that. You can also look at, let's say, another example would be tan 45 will be opposite over adjacent, so opposite over adjacent, which is just 1 over 1, which just equals 1. We can also look at the second triangle. You can do the same for the rest of the trig identities, so cos, cotan, secant, and follow the same rules. So here, if we said, what is sine, or sorry, let's use cos. Let's say cos 30 degrees. We know cos is CAH, so ca, adjacent over hypotenuse, so adjacent over hypotenuse, and we know it's square root 3 over 2. And let's say we want to do secant 30 degrees. So secant is just 1 over cos, so it would just be 2 over square root 3. And similarly for sine and the rest of the trig ratios. So here the outline kind of same idea, but they use kind of different variables to represent adjacent and opposite. And they kind of create a table for all the sides and all the ratios for the angles. So here, okay, so they go through a process to evaluate for the angles. And they go through some examples, so. All clear question, correct explanation. They don't really show the special triangles, so we'll take that out. Okay, let's go to the next question. All right, so find the value of a limit. So let's look at this image here provided. I think I might have opened this twice. Let's try that again. Okay, save. Just give me a second here. I just gotta fix something quickly. Okay, so we're asked here to find the value of the limit of the following. So sine 2x, cos 3x, tan 4x, and so on as shown in the question. And we have to figure out which answer is correct, A, B, C, D, or E. So we'll start off by writing down the question. So we're trying to evaluate for the limit of x as it goes to 0, sine 2x, cos 3x, tan 4x, over cos 2x, sine 3x, and tan 5x. So let me just move that so it's visible. Okay. So let's just double check that. Okay, so we have the same limit that we have to evaluate. So let's say we just substitute in 0 for everything, and we just evaluate it the normal way. We would get the following. So, excuse me. So we would get, if we had sine 0 is just equal to 0, and then cos 3x, so cos 0 would equal to 1. So we have 0 times 1. Tan 0 would just be 0. And then we have cos 0 would be 1, sine 0 would be 0, tan 0 would be 0. So we get 0 over 0, which is undefined. So here we would be incorrect to say it's undefined. We have to follow a different process to find the limit. So here we would use L'Hopital's rule. So let me just give a quick definition of what L'Hopital's rule is. So usually when you see a situation where you have 0 over 0, you would use the following property of a limit. So the limit of x as it goes to z of some function f over some function g is equivalent to the limit of x as it tends to some constant c of the derivative of the top function over the derivative of the bottom function. So here, that's what we're going to do. We're going to take the derivative of the top and bottom. So let's clear some of the board here. Okay, so give me a second. All right, so the first thing we do here is we split up the function into separate components. So we'd say the limit, we'll take the cos and we'll keep them together. So cos 3x, so x goes to 0, cos 3x over cos 2x, because we know we can evaluate for this, times the limit x goes to 0 of sine 2x over tan 5x times the limit of x goes to 0, and we have the final one here. So we have tan 4x over sine 3x. So we can see how these two are equivalent. We just kind of split up the limit into 3 separate limits. And now we're going to use L'Hopital's rule. So for the first limit, we don't really need L'Hopital's rule. It's just 1 over 1. Because cos 0 is just 1, so it'll just give us 1 over 1. And then the second one, we'll have the limit of x to 0. So the derivative of sine 2x will be 2 cos 2x. The derivative of tan 5x is 5 secant squared 5x. So we know that the derivative of tan x is secant squared x. So here we're just going a little further. We do the derivative of tan, and then we do the derivative of the inside component, which is 5x, which is just 5, and that's how we get the 5 in the front. And then finally, we do L'Hopital's rule again. So we have the limit as x goes to 0. We get this top is 4 secant squared 4x over the derivative of sine 3x, which is just 3 cos 3x. So now when we evaluate, so this is the first component is just 1, and then the second component, 2 times cos 0, which is just 1, over 5 times secant squared secant squared 0. So we know that secant is just the inverse or the reciprocal of cos. So this will also give us 1. And then this limit will give us 4 times secant squared 0, which will be equal to 1, because we know secant is just the reciprocal of cos, and they both give us a 1 when we evaluate at x equals 0. And then finally we get 3, and then cos 0 is just 1. So we're left with 2, so all the 1's go away, and we have 2 times 4 on top, which gives us 8, and 5 times 3 on the bottom, which gives us 15. And that's our final answer. So that's our final answer. Right here. Okay, so looking at the solution. So they identify that you have to use L'Hopital's rule. Let's look at the options. So here B is the correct answer because we got 8 over 15. So here they select the correct answer. They don't show their work, however. So correct answer selected. Did not show the steps. Solution. So here the solution is incomplete. Okay. So here the question is asking us to define the geometric figure, square, and rectangle. So we want to define the properties of a square and a rectangle. So we have a square. We'll start off with a square. So first property of a square is that we have 4 sides and they're all equal. So all sides are equivalent, so we just labeled them as A. We know each angle is a right angle in a square. We know that the diagonals of a square are equal in length. And they bisect each other at the midpoint of the square. And finally, they bisect each other at right angles. So in my picture, it's not clear that they bisect at right angles, but they do. So if you were to measure this angle right here, it would be 90 degrees. So those are the properties of a square. For a rectangle, we have something like this. A rectangle has the following properties. So opposite sides are equal. So if you had side A and side B, those 2 sides shown are equal. Each angle of the rectangle, similar to a square, is a right angle. Diagonals of the rectangle are equal. So if we look at the diagonal here and the diagonal here, these 2 would be the same length. And then the diagonals of the rectangle bisect each other, and we know over here would be the midpoint of the rectangle. So here we can see that the description of a square can also pass for a rectangle. So we can say a square can also be a rectangle, But a rectangle is unique and it can't really be a square because it has different sides. So if we had a rectangle, sorry, a square, it would have equal sides. So it satisfies the requirement for a rectangle because we have both sides are equivalent. So this side and this side are equivalent, and this side and this side are equivalent. But it doesn't go the opposite way around. So we can't say a rectangle is a square, but we can say a square is a rectangle as well. So it satisfies the properties of a rectangle. So here the description of what a square and a rectangle here is correct, and they identify similar properties. Yeah. Solution. Great job. On to the next question. So this question is asking, so Jangles Corporation receives $20,000 invoice. So we have 20,000. March 3rd. The cash discount terms are 310 and 30. So 310 means just 3% discount. I'll just say D. If the payment is given within 10 days, so that's what, so 310, this means 3%, this means within 10 days. And then we have net 30 for the total payment. So you have 30 days for total payment. On March 10, Jangles sends a partial payment of 12,000. So 12,000. What credit should Jangles receive for the partial payment? So because the difference between March 3rd, so over here March 3rd and March 10th is less than 10 days, they would get that 3% discount, which we would have to add on to the 12,000 payment. So essentially what we have to do is 12,000, we would take the total, so we have the total payment that is required, which is 20,000, and subtract the 12,000 payment plus the 3% discount on the 12,000. So I'll just write it down here. So plus 3% of 12,000. So 12K. And that's all in brackets. So calculating this gives us 20K minus 12K. So just K for meaning 1,000. So 20,000 minus 12,000 plus 3% 12,000 is 360. So here 20,000 minus 12, 360. So this is how much should be credited on the invoice of 20,000, and the balance that we'd get from that, if we put it in our calculator, we'd get 7,640. So really the question is asking us for how much credit should Jangles receive for this partial payment. So we'd say $12,360 of credit should be received. So that would be subtracted from the invoice, so the cost that they have to pay, and that would give you the balance of 7,640. So here similar process is formed. So within 10 days of receipt of invoice, hence it will be entitled for a discount of 3% on 12,000. So they calculate that and they get 360. So the amount of credit Jangles should receive for this partial payment is 12,360, and we know that the balance would be 7,640. So here solution is correct. Great work. Alright, so here we're given an image to find some value for something. Let's open up this image. Let's give it a second to load. Save. Let's open up this image. So we're given an integral. So we have to find the value, or so we have to just evaluate the integral for this function. So I'll write that down here so we can evaluate. So I just wrote down the same integral that was in the question. So x times e to the 3x dx. So this is an integral that should be evaluated by integration by parts. So to refresh your memory of what integration by parts is, so if we had in the integral of u dv would give us, or would be equal to, uv minus the integral of v du. So this is just the standard formula for integration by parts. So we'll use it to evaluate. So here we essentially just have to define what u and v is. So we'll define here u as x. So x over here. And then we'll define, so if we take the integral du, or sorry, if we take the derivative of this, we get du is just dx. And then we'll define dv. So we'll define dv over here as e3x dx. So that will be e3x dx. If we take the integral of this, we would get v is 1/3 e3x. So now we've kind of figured out all the components. We know what u is. U is right here. dv. v is right here. uv here is u over here and v over here. And then we have v du, so v and du. So here we just have to kind of substitute in the values into the integration by parts formula. So substituting these in, we would get, so this down here is equal to x 1/3 e to the 3x. So this is u times v minus the integral of v, which is 1/3 e3x times du, and du here is dx. So we'll just write dx. So now we'll just kind of simplify and evaluate the integral. So here we still have 1/3, or what you say, x/3 e3x. And then we'll take the 1/3 to the front, and then we have the integral of e3x dx. So e3x is a simpler integral to evaluate than x3x up here. So doing this, we have x/3 e3x. And then we have negative 1/3. And then the integral of e3x is 1/3 e3x. So now, and we have to have the constant c at the end, so dc. Sorry, so for whenever we evaluate integral, we have to add a constant at the end. So here, the next step in this solution is x/3 e3x is minus 1/9. So a third times a third is just 1/9 e3x plus c. So this is the final answer to evaluating the integral. So here it identifies that we have to use integration by parts, but no solution is present. No solution is present. Use integration by parts to get the result as follows. We get 1 over 3 x times e to the 3x minus 1 over 9 e to the 3x plus c. So that's the value of the integral. Okay, so there was no solution present and we provided the correct solution. Let's go on to the next question. Okay. So this question is asking just how do you integrate? So this is a very broad question. Integration kind of is used with numerous functions. You can kind of go through some examples here. So here in the solution, it provides multiple examples of integration. So here we know that the integral of sine x is negative cos x plus c, so you always add a constant at the end. The sine and cos integrals are kind of things you just have to memorize. This one over here is probably one of the most important ones. So we'll do an example of that. So if we had y is equal to xn and we want to evaluate the integral of xn of this function, so we do the integral of xn dx, where n is just any kind of whole number, or any number actually. We would get the following. So we get x to the power of n plus 1 over n plus 1 plus c. So this is kind of the standard formula for evaluating kind of a function represented with x values or x variables. So we can go through a simple example. So if we want to evaluate for the function x squared plus x plus 1 dx, so we use this to evaluate. So x squared, the integral of that will just be x cubed over 3. So if we substituted 2 for n, we get x to the 3 and then 3 at the bottom as well. So you can see how this formula makes it easier to evaluate. Then the next component, x, would just be x squared over 2. So the exponent here is 1, which is n in our scenario, and then n we substitute into here and here. So we're left with x squared on top and then 2 on the bottom. And lastly, 1. So for 1, the exponent is actually 0. So it will be 1 times x to the 0. And we know x to the 0 is just 1. So we substitute 0 for n. We get x to the 1. And then 0 on the bottom would just give us over 1. So we just get plus x. And then we just add our constant at the end. So that's just one of the examples of how to integrate. There's many other ways or many other functions and kind of identities or properties that you should memorize for integration. So another one is the integral of e to the x is just e to the x. That's another useful one. And then here the solution provided shows integration by parts and so on. And they show you kind of more complex integration. So usually when there's a specific question, it's easier to show the solution. Integration is more of a general topic. So the solution outline to a general overview of integration. That's correct. Great job. Please give a more specific question. So one thing I also wanted to outline for the previous question is that for integration of a function on a plot, what it's essentially doing on this plot, so some function f at x, the integral will be calculating the area underneath that function, so between the x-axis and below the function line or curve. So that's what it's essentially calculating. Okay, so on to the next question. What are the domain, range, and asymptote of the following function? So if we had the function g at x equals 0.5 power of x minus 9. So a domain is a function, or the domain of a function is the set of input values for which the function is real and defined. So in this scenario, for any x value that we substitute here, so 0, 1, 2, 3, 4, or negative 1, and so on, we would get a value for y. So here the domain is just all real set of numbers. So let's say the domain is all real set of all real numbers. The range or the asymptote, how we want to define this is we start off by rearranging the equation. So we'll say this is, so g at x is also equal to y. So we'll just erase this and we'll just say this is y for simpler notation. And we'll rearrange the function to get y plus 9 is 0.5 power of x. Take the log of both sides. So log y plus 9 equals x log 0.5. So we just move the exponent down to the front. That's one of the properties of logs. And then we isolate for x. So log y plus 9 over log 0.5. So the main reason we're doing this is to see if there's any asymptotes. So by solving for x, we've already solved for y up here, and we kind of can see that there's no asymptotes. And the range for x is all kind of real values. For y, however, we can see that for log, the property of log is that this value over here cannot be greater than, sorry, it has to be greater than 0. So y plus 9 has to be greater than 0. Because that's just the property of log, so this gives us kind of a limitation for this function. So y has to be greater than negative 9. And we know that that means that y equals negative 9, there's an asymptote. So y equals negative 9. So this is one of the asymptotes. And we know that this is kind of the range in the y-axis. So I believe there's a graph of what this looks like. So we can kind of see over here that when it reaches negative 9, there's no values below. So if we substitute y into this equation, we can't substitute anything equal to negative 9 or below, but we can substitute anything greater than negative 9. Similarly, for x, we can see on the graph, so any value of x here, there's a y value associated with it. So this would give us that for any x value, we get a y value. So here we can say that that an asymptote exists at y equals to negative 9, and the range for this function is y has to be greater than negative 9, and then x could be from negative infinity to positive infinity. And then the domain is just the set of all real numbers. So just looking at the solution now, as x tends to positive infinity, then y tends to negative 9, as y equals negative 9 is the only horizontal asymptote. So they go through a similar process for isolating for x to get that y equals negative 9 is an asymptote, and that y is greater than negative 9 is the range in the y for the function. So here the solution is correct. Great job. Okay, so this question is asking to integrate e to the power of 2x. So evaluate the integral e to the power of 2x dx. So we have to evaluate for this integral. So we can use the substitution method. So if we set u equal to 2x, we know that du is equal to 2 dx. So we can go through this process. Also, the other thing to know that the integral of e to the x dx is equal to e to the x. So we can kind of keep this in mind as we solve. So if we substitute in the values, I'll write this down here. So the integral of e to the u, so we'll put the 2 in the front. So if we substitute for dx over here, so we substitute it in, and then we have to rearrange this. This means dx over, not over 2, is equal to du over 2. So du over 2. So we can bring up the half to the front, so we'd say a half integral of eu du. We know that the integral of eu is just eu, so 1/2 eu plus a constant. And we'll substitute in u equals 2x, and that will give us I'll give us a half e to the power of 2x plus c. So we did substitution. This integral doesn't necessarily need you to go through substitution, but substitution is just an easy way to demonstrate how to evaluate this integral. Essentially, we could have just looked at this component of the integral, and we know that the integral for e to the x is just e to the x. So we know that this component will be there, but we also need to take the above into consideration. So if we took the derivative of 2x, we know that the derivative of 2x is 2, and we have to multiply that by this function. So if we were to take just the derivative of this, we would get 2 in the front, so we take the derivative of this and we multiply it in front, and then we have to take the derivative of everything of the rest, so we have a half e to the 2x, and then the derivative of a constant is just 0. And we can see how this simplifies down to e to the 2x. So over time, you can kind of recognize this, and just, instead of using substitution, you can kind of just go right away to the final answer. So looking at the solution, the correct process is followed to take the derivative. So here they use substitution, u equals 2x, and then du is 2 dx. And they get a half e to the 2x is the right integral. So correct answer. Great job. Okay. Okay, so that's all the questions that we had time for this session. Hopefully you found this helpful, and if you need any more homework help or tutoring, you can always visit the link in the description or go on oneclass.com and see how other solutions are solved. I'll see you in the next session. Goodbye for now.